Hi everybody, this is David Paul. I'll introduce myself in a little more detail here in just a moment. Thanks so much for attending. So we're going to talk about how to reduce the cost of RO water treatment. Today it's about a 40-minute presentation. Maybe it won't be that long, but around that, and the rest of the time will be for Q&A. So if there are lots of questions, then we'll go to the end. If there aren't too many questions, then we'll just quit when the questions have all been answered. So type your questions in the question box, and then at the very end there'll be a Q&A session, and I'll read the question and then give my answer. So when we're talking about cost reduction, it really is site-specific. So in a webinar like this, all I can do is really give you some areas to look at, but you have to know your own cost in your local area, your own plant, and you'll have to figure out the cost benefit, do a cost benefit analysis and figure out what's going to work at your facility. But of course, cost reduction is just about as important as anything we can possibly do. So this presentation is recorded. It will be available on our website, and you'll be sent a PDF copy of this presentation when you get your email, your thank you email tomorrow. So I'll go through my experience and then we'll talk about categories of cost reduction. So cost reduction has been a major role basically from the get-go for me. I started out in 1977 at an 1,800 megawatt coal-fired power plant that was a zero liquid discharge plant. So no water left the plant except through evaporation. So it took a lot of money, a huge system in order to make this happen, and cost reduction became a very big part of my job. I was 2.5 years as an operator, and then 1 year as a shift supervisor, and then 8 years as the manager of these facilities. This is not anything that's of that particular importance, but the process flow of that plant that I started out at was a fairly complex plant, about 3,000 gallons per minute total. So the RO unit was producing permeate for cooling tower makeup and also boiler makeup water. And then the concentrate from the RO unit went to brine concentrating evaporators. And then the slurry from that went to solar evaporation ponds. So you can imagine there's a lot of cost here. In today's dollars, it was about $15 million a year for the annual budget for this system. Here's a picture of one of two of the water treatment systems. One other thing is that flow meter right at the front. We're going to talk about that in a second. And when we're talking about construction, one of the most important things is people. So I learned that as the manager of that plant, that the power generation company contracted and asked to evaluate the water balance of the power plant. So know where all the water went, how much water, what was the chemistry of it, and then design a zero liquid discharge system. Again, costs a lot of money. Well, I was a manager during commissioning and afterwards, and I found, looking at the flow meter, I found at times that the flows going into our ponds were way above design, and there was no way that we were going to be able to handle this. We were going to run out of a capacity. So I assigned one person every shift to do nothing but walk around and manholes. So there's a day every 2 days going out looking at manholes, and then they would find a high flow. We learned what wastewater flows went into every manhole. So within a few months, we became experts at water management at our plant, to the point that by doing this, we were able to reduce the wastewater flows almost in half. So as far as cost reduction, the lesson here is, had we done this before we designed this zero liquid discharge plant, we could have controlled the wastewater flows to the point that we only had maybe a half of the flow, and the actual ZLD system would have been much smaller, saving millions of dollars. So I want to stress that from the get-go that people are going to be your biggest resource. So then later on, when the company was really in financial trouble, we started a contest plant-wide, not just in the wastewater area, to pay employees for cost savings ideas. And the employee would submit an idea. If they needed help, they would get help from engineers or whomever. And then a team value each idea and then get a good estimate of the cost savings. The only ideas that were implemented were ones that would have a payback of no more than 1 year. And I think we're probably close to that situation now. Most plants aren't going to implement anything that doesn't have a payback, probably at least 2 years. But if you can get a payback in less than a year, then you're going to get people's attention. And the employees would receive one time 5% of the first year savings. And by doing this, and it took maybe 3 months to go through this whole process, but it resulted in over $1 million per year in savings. So again, people are going to be our biggest resource. Then in 1988, I left that company and formed this one for training consulting. So I've gone into hundreds of plants here since 1988, basically just about every industry, and saving millions of dollars for our clients. So they're out there. Cost savings are out there at your plant, so you just know where to look. So that's what this webinar is about. Is we're going to talk about cost savings areas. And then we actually have some details on some of the jobs that we've done for cost savings. You can go on our website and get some details. So as far as the categories, I started out with people, and we'll just have another slide or two on people. We'll look at power. We'll look at 9 different areas, and there are more to look at, but we only have an hour here, and the presentation will only be like 40 minutes. So we'll just cover this. So as far as people, your people, our people know where cost savings are. I mean, the people that are operating the plant, monitoring the plant, like plant engineers, these are the folks that can figure out where you have the cost-saving opportunity. But we do have, the more people are trained and the more that they are proficient in all the duties of their water treatment jobs, that is the best, because operator or personnel errors can cost a lot of money. So investing in training can be a really good return on investment. Power is another big one. Power is frequently the highest cost for our water treatment. And at some places, power costs can vary from hour to hour, season to season. Many areas you have higher costs during normal working hours, like Monday through Friday, 8 to 5, and then there may be a cheaper power rate in the evenings and even a cheaper one in the middle of the night. So those are opportunities. But if you just look at the kind of money at 10 cents per kilowatt hour, and that's cheaper than most will have. I mean, there are places like in the Caribbean islands where they can go over 30 cents a kilowatt hour. So power is going to be something that always we look at for anything that any cost reduction idea that we have. Does it involve reducing power? Because all we have to do is know the rates and we can figure out the cost savings. So at 10 cents per kilowatt hour, if you're using 1,000 kilowatt hours, which is about what a home uses per month, then you're talking about 100 US dollars. Well, 1 horsepower, if we're talking motors, 1 horsepower is 745.7 watts. So times 24 hours, you have 17.9 kilowatt hours. And at 10 cents a kilowatt hour, then that's $1.79 per day. You say, well, okay, $1.79 per day. Well, that's not much. Well, what if you have a 100 horsepower motor, and many of you have motors bigger than this, and you have many of them? So if you have a 100 horsepower motor running 24 hours a day, that's 179 US dollars today per day, and times 365 days, that's a whopping $65,000. So, you know, if you find something that can knock off 10%, all right, and it doesn't cost more than $6,500 for this particular example, then you get a payback in a year. The other thing that is scary about this is even a power price going up a cent. You know, that's a 10% increase in the power cost if you were at 10 cents per kilowatt hour. So just a little increase in power cost can really hit you in the pocketbook hard. So we need to look for projects that can save power. Already, you know, this may not be available to all of you, but for some, it's certainly, you know, this is going to be a higher level decision, but there are huge plants today that are running 100% at night and less during the day, just to keep the cost of power down. And another thing that you might not think of, but when you have problems, such as fouling and scaling problems, and that causes your pressures to go up, that pressure really equates to power costs. So the more pressure you have to supply, then the more you're paying for power. So all of that needs to be factored in. If you can find ways to keep fouling and scaling under control, you'll have less power usage, and that's a cost savings. Waste heat, if you do have any waste heat available, waste heat for warming, like an RO feed water, here's just an example, RO on a 2,000 milligram per liter well water or a surface water at 50 degrees Fahrenheit, and this is just an example using one specific membrane, you're having to supply 290 psi, so that's 3.5 kilowatt hours per 1,000 gallons for kilogallon. So kilo means 1,000. At just 27 degrees warmer, you're knocking down 100 psi, and you're like at 2/3 cost on power. So if again, if you have waste heat options, if you're dumping heat down the drain, that might be something that could be cost effective. I'm going to talk about water minimization and wastewater minimization together. Here's an example. So many industrial clients are purchasing municipal drinking water as their raw water. So they're paying a municipality both for water coming in and for wastewater going out. So this is last year, City of Houston, and this top part's not really of interest, but if you go up to a 10-inch pipe coming into your plant or going out, then here's just the base rate. So that's not much. I mean, 177 times 12 months. So not a lot of money. Here is where you're getting hit. So $3.92 per 1,000 gallons, and the wastewater is even more expensive. So if you just do the math on that, if you have 100 gallons per minute of feed water, so you're purchasing 100 gallons a minute, some of you will purchase more, some of you will purchase less. But 100 gallons a minute times 1,440 minutes per day, you end up with 144 kilogallons, 144,000 gallons per day. And at the price quoted in that table, you're looking at $564 per day fee and $200,000 per year fee. So anything that you can do that minimizes the amount of raw water that you need, you can use this as a basis for implementing the project. And the same thing, anything that you can do to minimize wastewater production, you can use your fees that you have in your area. You can use those to justify cost reduction projects. Other things as far as water and wastewater minimization, if there is a cost-effective way to recycle certain water, so recycle using it for something else, you can, like ROs at startup, typically for higher purity systems, your permeate dumps to drain for a minute, 2 minutes, 3 minutes. You have a post-shutdown flush. You have the startup flush. So that can be a significant amount of time, especially if you're stopping and starting an RO unit several times a day. So if that's just going down to the sewer right now, well, you look up your sewer charges and say, okay, this is costing us X number of dollars and cents per 1,000 gallons, and we have this many 1,000 gallons going down the sewer. Can we justify, rerouting, recycling, reclaiming, reusing, doing something to get that water to reduce our water and our wastewater volumes? So we'll look at some examples for this. So a reuse option, filter backwash, concentrating, which is wastewater minimization, but really they go hand in hand. If you reduce your wastewater out, you may also be reducing your water in, because if you're concentrating, like you're putting in either higher recovery RO units or you have a concentrate recovery RO unit, then you're making more permeate. So if you're making more permeate, then you may not have as much water demand as you had prior to implementation. So also combining wastewater streams or treating them individually. So you may have a combined wastewater stream now. Is it cheaper to just sewer it, or is it cheaper to process it, or is it cheaper to look at each one of the flows that make up the wastewater flow, and would it be reasonable, practical, and economical to treat one or more of these flows separately prior to being combined into a wastewater stream? And then finally, I think that, if we look into the next 20 to 50 years, that more and more plants are going to be driven economically to zero liquid discharge. Right now it's not economical for most, but environmental regulations almost never get looser. They almost always get tighter and tighter. And as they get tighter, then things that weren't cost justified in the past become cost justified in the future. So here's just a picture of 3 multimedia filters. And if the backwash water is now going to the sewer, again, you can calculate what that's costing you, and does it make sense to treat that water and reuse it would actually be cheaper for you. This is actually quite common today. Let's say you have a 15-year-old plant, 20-year-old plant. You've had reverse osmosis in it for 10 or 20 years, or maybe from startup. And the most common off-the-shelf, cheapest RO units are typically 75% recovery for brackish water. And here we're seeing 4 RO units, and each one of them at 75% recovery, 100 gallons a minute of feed, 75 gallons a minute of permeate, and 25 gallons per minute of concentrate, or brine or reject, all three of those the same term. So you may have been sewering, in this case, from 4 RO units, sewering 100 gallons a minute. Well, we already saw that that's 144 kilogallons per day. So you got that fee that could be, you know, tens of thousands of dollars over a year's time. So it's actually fairly common today, since most of your drinking water RO units, so RO units that have a drinking water as a feed water. Again, many industrial clients purchase municipal drinking water as the raw water. So these reverse osmosis units are operating on pre-treated drinking water. Well, most drinking water can be concentrated more than 4 times, which is what you get with 75% recovery. So it's becoming common, and you'll see it quite often, that they'll cost justify putting a secondary, usually called a concentrate recovery or just a recovery RO unit, and it may still be just a kind of an off-the-shelf 75% recovery system. But if you're able to do that without scaling the RO unit, then now you've gone to 94% recovery. So now you've gone from 100 gallons a minute going to the sewer to 25 gallons a minute going to the sewer. Of course, you always have to make sure that what you're sewering meets local requirements. But all of that goes into you figuring out what is going to be cost effective at your plant. So there are some other water and wastewater minimization areas that you can look at. Some places can recycle wastewater. So if you had RO unit 75% recovery and the concentrate coming out was really not that bad because your feed water was drinking water, then you might be able to do lawn irrigation. There are plants that either send it to other people's fields, or they've actually purchased fields. They do their own irrigation. But you can, you know, look at different places around the plant, around the area, that allow you to take some of these wastewaters and use them in different applications. So again, the name of the game is cost reduction with a payback of a year or less. That's what you're shooting for. Occasionally your cost savings or your a costly problem may be due to design. Poor design certainly can cost money, and since we're talking about RO water treatment, having an inadequate RO pretreatment, especially for fouling, particulate fouling control. So a good, or I should say an adequate RO pretreatment system from a fouling perspective is one that can give you a silt density index, an SDI, of less than 3, 24/7, 365. So that would be today's standard. So if we have under-designed media filters, in other words, the loading rates are too high, so you just don't get the particulate removal that you want. You have a high fouling RO unit design. You don't have enough membrane in it. They didn't give you enough membrane. They didn't give you enough pressure vessels and membrane elements so that your water flux rates are too high and or your cross flow rates are too low. These are design issues. not having an adequate pre-post shutdown flush. Occasionally you don't even have them, especially for the post shutdown flush. And then also that the design of the cleaning equipment for the RO unit is inadequate. So, and then inadequate instrumentation for monitoring. And then for the operation area, I'm going to take for the next few, I'm going to take 3 examples for each. And these are the examples that I see in more places over the last 20 some years. So this is very common in some plants, that you're designing your water treatment system, you're designing the capacity of the system based on worst case. So if you're from the power industry, it could be a tube leak. And during that time period, you need everything you can get. You need all the water you can get. So you've got, in this case, 4 RO units putting out 400 gallons a minute, or cubic meters per hour. For those of you that are using metric, 100 gallons a minute doesn't equal 100 cubic meters per hour, but I'm just trying to make it easy on the brain. So no matter what units of measurement you're using, we'll use 100 in this case. So if the plant needs worst case 400 gallons a minute, and that's what was designed, yet most of the time the plant only needs 200 gallons a minute. Now you're having to idle RO units. You really don't know when the problem is going to occur, so it's not like you can just unload elements and just shut them down. But it causes a problem. There's a cost associated with this. There's going to be a cost with preservation, or a cost for cycling, and also a cost for bio, especially if it's a surface water plant and the temperatures get into the 70s, 80s, and 90s. This is also very common that the RO system is going to come on and off based on storage tank level. So if the level drops, the RO unit comes on, the level goes up, and it stops. Well, when it stops, you don't have the feed concentrate shear force to keep fouling, especially bio, under control. So it may end up increasing your cleaning requirements, which means if you're biofouling, it means that you're going to have higher pressure to make the same amount of permeate. So that's going to increase your power requirement. And the more you clean, the less membrane life you'll have. The second area was variable flow rates. RO units really shouldn't be operated, in my opinion, with variable flow rate. So whatever the design flow rate is, you operate the RO unit at the design feed permeate concentrate flow rates, or you turn it off. And the reason for that is varying. It changes water flux rate, so it changes the fouling and scaling potentials, and it changes the cross flow rates. Both those two impact fouling and scaling potential. A little thing like this, you've got a high pressure drop across the first stage of your vessels. You don't really know how many of these elements are in bad shape unless you take them out and weigh them or do something to determine which ones are highly fouled. So if you were just to make the decision, okay, we don't have enough money to replace all of them, we don't really know how many are that bad, and you put a new element in the first position, that would be the kiss of death, because the water flux rate then on that first element, because of the back pressure of the two dirty or fouled elements behind it, would make the water flux rate so high on that first element to what it was before you replaced that element, just a few weeks. So not a good idea. On the metric end, the 3 problems I see most commonly are not trending performance, not measuring pressure drop across each stage, and instrument calibration. So all of these are going to cost you money. These are things that if you're not doing, doing them. So we want to catch problems at an early stage, because that's probably when they're going to be able to be fixed the cheapest. So by implementing trending, if you're not doing it now, for surface water, for sure, always you need to be doing this. Certain well waters that don't change temperatures, don't change, deep well waters, you can get away with just not in the normalized data. But everybody else needs the normalized data that's on surface water, or if there are any changes in the well water, superficial well. And then the second one was measuring pressure drop across each stage. And most people that are monitoring using the trending programs are using the membrane manufacturer's free program. So here's Dow's, but you can see here they only put in feed pressure and concentrate pressure, so it gives you a pressure drop across the first stage. Well, we want to know which stage the problem is located, whether it's in the first stage or second stage, so we know where to clean and where to fix the problem. So you have to, add another column in here or two, and be able to monitor pressure drop across the first stage and second stage. And then lastly, instrumentation calibration. That can be very cost effective, because we are relying, especially our scaling and fouling potentials, we're relying on these instruments, so we need to make sure that these are calibrated. And then the next area is chemical cleaning. And the three problems that I see more often than any others is waiting too long to clean, too small of a cleaning pump, and not cleaning back to new or near new performance. If you wait too long to clean, then the elements themselves, one or more elements, can become channeled. They get so plugged that now you have little channels, just like you get in a media filter. If it gets slimed up or stuck together, the media gets stuck together, you start getting channeling. Well, that happens with the RO membrane elements as well. So when that happens, you're just not going to clean them. So this is going to cost you money in power. It's going to cost you money in membrane life. So making sure that we get the best chemical cleaning possible, that's going to be very important in reducing cost. The inadequate cleaning pump, a lot of places that I've seen where the pump is big enough to clean the second stage, but really cannot get the flow rates needed for all the first stage pressure vessels, because most of the time you have about double the number of pressure vessels in the second stage in the first stage. So first stage may have 10 pressure vessels, second stage have 5 pressure vessels. You just need to make sure that you can get an adequate flow rate, especially for fouling, because too low a flow rate is not going to be effective. So here is a real world example. This is a extremely high extremely high fouling feed water. We can see here where here's basically new performance, and there were a couple of cleanings. Here's a cleaning that did not go back to new performance, but the next one did. This particular plant has a variable feed water. It's an industrial wastewater. It's nasty stuff. So what works one time doesn't necessarily work, because at this particular plant, this particular cleaning that took it back to new performance basically was tried many times and did not work ever again to that point. So but at this plant, the feed water, the wastewater coming into it changes so rapidly. This is industrial wastewater, oil and gas wastewater. So at any rate, this is the ideal, because if you don't do this, even if you don't have a horrible fouling water like this, if you don't clean it back to new performance, then you really are going to get shortened membrane life, and that's going to cost you money. And then finally, reduce chemical usage. We'll look at just 3. Bleach. and a dechlorination agent, which is usually sodium bisulfite, sodium metabisulfite, sodium sulfite, something like that. Some sulfite for dechlorination is the most common. And then scale inhibitor. On chlorination, if you're doing it, if there's any way not to do it or to minimize it or to chlorinate on an intermittent schedule, not a continuous schedule, that can save a huge amount of money. I've learned this over the last 27 years that chlorination and dechlorination is one of the biggest problems in membrane water treatment, mainly for RO, mainly NF and RO membranes, but chlorination, dechlorination creates food for bacteria that weren't there, and as soon as you dechlorinate a chlorinated stream, then the bacterial growth can be astronomical. So back when I started consulting back in 1988, especially like in the Middle East or the Caribbean, it was just common to continuous chlorinate seawater RO units from the intake and then dechlorinate just at the cartridge filters before the high pressure pump of the RO units. And these systems were just unbelievably foul. You're cleaning them once a week, once every 2 weeks. Membrane life is a fraction of what it should be. And now you have the largest seawater plants in the world. The 3 biggest ones in Israel do no chlorination whatsoever. So if you can reduce or eliminate chlorine, that will reduce the biofouling downstream. And then sulfite, if you underfeed, if you don't feed enough sulfite to get rid of chlorine, so this is in a plant that actually does have chlorination upstream or is purchasing chlorinated drinking water from a city. If you underfeed, then you'll cause membrane damage, but overfeeding can cause increased biofouling. And with that, then you have the increased pressures, you have the increased chemical cleanings, and increased costs with that. And then finally, anti-scalant or scale inhibitor. We want to make sure that we're not pumping more than design. It's not going to help as far as scaling is concerned to pump more. It's not uncommon that on surface water supplies that the design may be to pump your scale inhibitor in at the worst case ever seen, which could be 10-year drought, something like that. So you may be injecting more than you need, but this one really takes somebody doing some research. This isn't something where you just go crank down on the scale inhibitor dosage. You need to understand the feed water, but it can be done. There are plants that have done the research, big plants that I'm thinking of, that have done the research, and some of them have saved hundreds of thousands of dollars per year. Okay, so there are many others, but we can't go into any others today. So in conclusion, we looked at 9 different areas with people in power being number 1 and 2, areas to look at how we can reduce costs at an RO water treatment system or really any water treatment system. So if you want more details, actually have a new seminar next January on how to reduce, where we go into this in much more detail with many more workshops and having you figure this out. And we have done this many times, many plants. If you bring us in, it's going to be a minimum of $10,000. If you come to the seminar and then you go back and figure out the cost reduction, then that's going to be the cheapest way, and that'll be one of your first cost reductions right there. So thank you very much. I appreciate your attention, and we will now go to Q&A. Okay, so question number 1. When it comes to chlorinated feed water, we dechlorinate it, but what about chlorine dioxide for a biocide? This is very interesting. Chlorine dioxide, I think, has potential. I recommended chlorine dioxide at one plant, well, probably 20 years ago. It doesn't produce as many food molecules as bleach does, but I think the jury is still out. There was a doc from GE, oh, it's been 2 years ago, maybe 3 years now, that published a paper on 5 different RO plants that were using continuous chlorine dioxide, and it was either 2 or 3 zero problem. I think it was 3 of them were zero problem, and 2 had some membrane damage, and this doc thought that it was due mainly to the pH control, that there's something about pH and chlorine dioxide. So I would just say that that is a possibility. So but that's all I can tell you. You would have to talk to the chlorine dioxide vendors, see what kind of guarantees you can get. Always best to pilot if you can. Pilot test small, as opposed to exposing a large, maybe even multi-RO unit system for something like this. But I think that we'll probably see that, but still the jury is still a little out on that. I don't think we understand what kind of interactions and what can cause damage of RO membrane with chlorine dioxide and what doesn't. And the next question, will ozone damage RO membranes? Yes, any oxidizing agent will. Ozone is a much more powerful oxidizing agent than chlorine is and bleach. So yeah, ozone would damage RO membranes even quicker. Next question, how much % cost can be reduced by applying RO water treatment? Again, every time you're talking cost, it's always going to be site specific. So if you're in the Middle East and you have to ship barrels of chemicals to your site, that's different than if you're somewhere else and you're a larger plant and you have a tanker load, you know, all the different prices. But I can tell you that that in my experience, that ion exchange, like full train ion exchange, and there's still some plants out there that have full train ion exchange, which would be cation, anion, and mixed bed ion exchange. Replacing the cation anion bed with RO, even as late as, it was probably 2 years ago, the last one that I was involved in, you get a payback in a year or 2, just with reduced regeneration chemicals. But so that's about all I can say. If you want to ask a different question on that, that's fine. Okay, next question. What do you think of the pump turbine energy concentrate recovery? I'm assuming you're talking about a turbo energy recovery system. So ERI has one. They purchased from, I don't remember the name of the company now. But the energy recovery devices, I won't say that one is better than the other, but you've got the turbo, which I think is what you're referring to here, and you've got the Pelton wheel, and you have the positive displacement type. So they're all good. They all will quote very high energy recoveries, you know, in the 90s, 90%, 90+%. They always fight with each other about who has the best, but they're all good. So I don't have any problem with the turbo energy recovery system. And Can sulfite, the next question, can sulfite encourage biological growth? Yes. Excess sulfite can. So we did research, this has been many years ago. We did research a couple of different plants when we were learning about chlorination, dechlorination, and what we found is that excess sulfite up to about 10 ppm or milligrams per liter increased biological growth. So if you were overfeeding 1 ppm, you had more bio. You overfed 2 ppm, you had more bio. It wasn't until you got to over 10 milligrams per liter that you actually started slowing down bacterial growth. So it's definitely something that can save you money, that if you'll just dechlorinate. Again, chlorination, dechlorination on surface water is almost always, especially surface water that gets into the 70s, 80s degree Fahrenheit. It's almost always going to be a challenge for biofouling, and biofouling is going to increase your costs pressure-wise, energy-wise, and also with the chemical cleaning-wise, and also with reduced membrane life. All right, the next one, intermittent chlorination is still used at the intake in the Middle East. What is your view on that? I love it. So when you're on seawater, you have to control mussel mollusk growth in your intake pipes. I mean, these guys will just almost close off the pipe if you give them a year or two of growth. They just layer upon layer upon layer, and your pipe gets smaller, and your pipe ID gets smaller and smaller and smaller. So you can't allow that to happen. And research has shown for most of these clam, mollusk, mussel types things, these bivalve types of critters, that you hit them with chlorine and boom, they'll slam shut. But just like us, they have to breathe, so they can stay shut for about an hour. So as long as you're chlorinating for an hour, 2 hours, there are plants in the Middle East that I'm aware of that chlorinate once a week, and they may chlorinate 1-2 hours. And for that time period, if you have to run your RO units, okay, then you run your RO units knowing that you're increasing fouling, but you're only increasing fouling for 2 hours a week. So that's, and then as soon as you shut that off, then the food goes away. So if any new biogrowth was initiated during those 2 hours, you really don't have the food after that to support it. So I'm really a fan of intermittent. Okay, the next one is UV light economical in controlling biofouling on membrane? That's another outstanding question. I think from my experience, and I'm going to say maybe 30 plants, somewhere in there. Not all of them that I actually went in and consulted, but in talking with plant personnel, I'm going to say that most, by far the majority, I want to say 25 to 30 of those, 25 to, let's say, 28 of those, it didn't matter whether the UV unit was on or off. The fouling of the RO unit was exactly the same. And the reason for that is really food. It doesn't matter if you kill every bacterium going into a RO unit. So for those of you out there that have ultrafilters in front of your RO unit, you're removing essentially all bacteria. So if you have a UF in front of an RO unit, you basically don't have bacteria going into your RO unit. So you would think, okay, there's no way you can biofoul. But that's the wrong way to think about it. It's all about food. Dissolved food molecules go through a UF. The bacteria don't. And since you never had a sterile system downstream, if you're feeding food to your downstream RO unit, you can have massive biofouling. Two of the top 5 biofouling systems I've ever worked with had UFs up front. So as far as coming back to the UV, I have had at least 2, maybe as many as 5 in the last 27 years, plants that said yes, they really could tell the difference between when the UV was on and the UV was off as far as fouling control is concerned. So there may be some things in certain waters that make a difference. So that's all I can say on that from my experience. And the next question was on UV2, so I think I got that. Here, there are many instrument suppliers. Any preferred suppliers? No, I wouldn't say that to a group. I work with all of them, so I don't want to make them mad at me. I think that's, let me see if there are any more. Scroll down, but I think that's all the questions. Yeah. So that's the last question. So we're a little bit early. Hope you're not disappointed that we're getting out. Oh, let me, hold on a second. Another question came in. Nope, no more questions so far. Okay. All right, so thank you so much. And we will have webinars at least once a month. We have one on power generation water treatment coming up next month. We're having a couple in over the next 3 months, maybe even one a month for the next 4 months on emerging membrane technologies. So we have one next Wednesday, same time. They're pretty much always on at noon. You know, a lot of times they'll be on Wednesday, sometimes Tuesday or Thursday. But at any rate, the one next week is on a high recovery RO system. It's from a company called Desalination, and it's called closed circuit desalination. It's very, very unique. Not like anything you've ever seen if you don't know about this closed circuit desalination. They're able to go to high recoveries, and I don't have any financial relationship with them, so I'm not promoting them. It's just that I want to make sure our folks know of what's out there that's available that could help them with water and wastewater minimization. So if you're interested, next Wednesday, you might want to show up for that. So thank you so much, and Daryl will go ahead and end it.